Alright, let's perform a titration calculation. We're going to start with the strong acid, strong base counterparts. The reaction is still the same as you might expect for a weak acid. Simply stated, you have an acid reacting with a base, forming conjugate base and conjugate acid. And here, once again, you have to recall the list of 11 strong acids. If you're dealing with any of the 11 shown here, you have a strong acid. If you have any other acid that's not on this list, the acid can be assumed to be weak. Alright, so that's the list of strong acids. The list of the most typical strong bases are going to be the alkali hydroxide metals, although sometimes you could have the alkaline earth metals also being used, in which case the proportions may change a little bit in terms of the balancing coefficients. But the idea is this: if you react a strong acid with a strong base, you will fully remove all of the acid when you add the same exact amount of moles of base. And in essence, you will neutralize the acidic substance, thus yielding a pH equal to 7 at the equivalence point. And the same thing is true if you do it backwards. If you start with a strong base and you titrate it with a strong acid, and notice the difference here, this is now volume of HCl being added as opposed to hydroxide. The curve looks almost like a mirror image of the first one. The pH still will be equal to 7 at the equivalence point, so long as both the acid and the base are strong to begin with. So typically what we do in regards to strong acid, strong base calculations is to perform stoichiometry to figure out the concentration of the acid in question. But this could also be applied to weak acids too. But I just kind of want to walk you through the process so that you refamiliarize yourself with it. Alright, so your typical setup is going to have a known concentration for one of the reactants. You will have the volume added for that reactant, and you're going to have some initial volume of the second reactant that you start with, right? So the volumes themselves, so the volume of the HCl can be used or determined by prepping up the solution in a volumetric flask that's 50 ml in volume. And the volume of sodium hydroxide can be determined by reading the final and initial volume readings from the burette. The concentration of hydroxide has to be given from the beginning of the problem, otherwise you won't be able to do what we're about to perform. But in essence, because the equation is balanced 1 to 1, this is kind of one of the more simple cases to investigate. First of all, you start with the volume of the substance for which you have the concentration and volume given. That's the hydroxide. So you have 25 ml of hydroxide. If you divide this by 1000 to change the volume to liters, now you can multiply the volume by the molarity, because molarity stands for moles of solute over, there we go, moles of solute over liters of solution. So in essence, the molarity is nothing more than a conversion factor that allows you to enter the realm of moles for whichever substance you have the concentration given, right? But of course, it does require that you have the volume in liters and the concentration. And as long as you multiply those two together, you're going to get the number of moles of the solute, which in this case is sodium hydroxide. Okay, so multiplying volume by molarity gives us the moles of sodium hydroxide. Now here's where you use the balance equation, because you know that for every 1 mole of sodium hydroxide you have, or you use 1 mole of HCl. So that becomes your conversion factor. 1 mole of sodium hydroxide goes on the bottom, 1 mole of HCl goes on top. You cancel the moles of hydroxide, you now have moles of HCl. So what you can do here is get the number of moles like actually calculated, or since you're looking for concentration in molarity, and what you have right now is just the moles of HCl, all you have to do is divide it by the volume of HCl that you started with, which was the 50 ml. Change that to liters, of course, and dividing moles by liters will now give you the molarity of HCl. So this is your typical stoichiometry conversion when you're doing your titrations, your titration calculations or problems. Now I'm going to give you one that's a little bit more complex now in terms of the balancing coefficients. You have calcium hydroxide reacting with chloric acid. They're both strong substances, but in order to balance this, you have to put a coefficient of 2 in front of chloric acid because calcium chlorate has a coefficient of 2 for the chlorate component, right? So when you perform this calculation, you have the volume and the molarity for calcium hydroxide. So we're going to start with the volume of calcium hydroxide. We're going to change it to liters, so divide by 1,000. Okay, so that gives us the volume of calcium hydroxide in liters. Now you multiply the volume in liters by the molarity of calcium hydroxide, which is 0.750 moles divided by 1 liter of calcium hydroxide. So the liters of the solution cancel out. Now you have moles of calcium hydroxide. And what we're going to use is the balanced equation to switch over from calcium hydroxide to chloric acid. For every 1 mole of calcium hydroxide, we use up 2 moles of chloric acid. So on the bottom, we're going to have the 1 mole of calcium hydroxide, so the moles of calcium hydroxide cancel out. And on top, we'll have the 2 moles of chloric acid. Finally, we're going to divide the moles of chloric acid by the volume in liters of chloric acid that we started with. So we divide by 0.1 liter to ultimately find out that the chloric acid concentration was 0.495 molar. And this is how you typically utilize titration information to determine the concentration of one of the reagents, which technically is your unknown. Alright, I'm going to basically stop right here, and on the next video I'm going to start the process of titrations for weak acids and strong bases.